Okay, so in this lecture, we study the isomorphism theorems. Okay, the isomorphism theorems. Okay, so let us quickly recall the concept of a homomorphism. So, if you consider two groups, G and H are groups, let me first precisely give an operation to both. So let G be a group under this operation. I am not using the term addition because I currently let me not be such specific. Let this be star and let H be say cross. Okay, so let's yeah, okay, B groups. Okay, then a mapping a function from G to H which preserves these operations such that if I consider two elements from G, say G1 and G2, and I compose them with the operation on G, then I get f of G1, f of G2 composed with the operation on H. Okay, but that's called a homomorphism. Okay, so it obeys some sort of a linearity. So our obvious interpretation of a homomorphism will be under multiplicative operations because on a general note we consider groups to be multiplicative. So my obvious representation of a homomorphism will be of this sort. So f of G1 G2 can be written as f of G1 f of G2, right? Okay. Two important structures which come out of a homomorphism directly are firstly what we call a kernel of a homomorphism. So we are considering this homomorphism to have these structures. So kernel of homomorphism is basically, so this is called a homomorphism. Okay, this is called a homomorphism. So kernel of a homomorphism is the collection of those elements in G which gets mapped to 1 or the identity of H. So f of x is the identity of H. And this is a subgroup of G, right? Because if you choose any two elements out of kernel of F, if you choose A and B belonging to kernel of F, then what can you say about f of AB inverse? So it will break down as f of A and f of B inverse. Now f of B inverse is uh, f of B whole inverse. Okay. So now since A and B are both in the kernel, so f of A is 1, f of B is 1, so its inverse is also 1, so it's 1. This implies AB inverse is in the kernel of F. And it's obviously non-empty because 1 is in the kernel. These statements can be trivially proven because see f of 1 can be written as f of 1 dot 1, which is f of 1 into f of 1, but this is in the codomain group, so it obviously has an inverse of f of 1, so we can use the left cancellation, right cancellation, whatever, but it will give you f of 1 is 1. Using this, you can obviously show that f of A inverse is f of A whole inverse for every element A in the domain group, right? Okay. Let me precisely give the statement as well. We can prove this in this way. See, f of A inverse is f of 1, so it's 1. But f of A inverse is f of A times f of A inverse equals to 1. But then again, you can use the left cancellation to show that f of A inverse is f of A whole inverse. Okay. So this is a subgroup of G. One more structure which we get is the image of a homomorphism, which we denote as Im of F. So it is the collection of all the elements of the form Fx such that X is in G. Check that this is a subgroup of H, the codomain group, justify. Okay. These are very trivial properties. One important property which again comes out is that uh, yeah, let's talk about this. Let me just present it as a lemma. Let F from G to H be a group homomorphism, then F is injective if and only if the kernel of F is the trivial group or the identity group containing only the element 1. Okay, let's prove this out. Um, yeah, suppose it's 1 1. Suppose F is 1 1. So I need to show this. Let X be an element from kernel of F. But that would immediately imply Fx is equals to 1. But F of 1 is also equals to 1. But since F is 1 1, so that implies X must be equals to 1. But X was an arbitrary element chosen from kernel of F. But that will obviously equal 1. Therefore, kernel of F is just the group containing 1. Conversely, let the kernel of F be trivial group, and we're going to show that F is 1 1. So let F of X be is equals to F of Y, but this implies F of XY inverse is equals to 1 by properties of homomorphism. But this means XY inverse is in the kernel of F. But kernel of F contains only the element 1. So XY inverse must equal 1, but then by right cancellation, X is equals to 1. Right? Or you cannot use the term right cancellation, you can just say that by multiplying Y on the right. Okay. Therefore, F is 1. Clear? Okay. Let's come to the first isomorphism theorem. The first isomorphism theorem. Okay. So it states that let G and H be groups, and let phi be a map from G to H, which is a homomorphism. So let it be a homomorphism. Then G mod kernel of phi, or phi or psi, whatever, I don't exactly remember the name of it, whatever bit, is isomorphic to the image of G under phi. Okay. So this is the first isomorphism theorem. One more justification we would need here is that the kernel is a normal subgroup of G. But that's again a very easy exercise, right? I can just add it up here. Also, kernel of F is a normal subgroup of G. Okay, and it's obvious because see, if I choose the element of the form G K G inverse, where K is in the kernel of F, then what is F of G K G inverse? So it's Fg times F of K times F of G inverse. You can just break it pairwise, but F of K is 1, so it's F of G G inverse, but it's F of 1, so it's again 1. Therefore, GK G inverse is again an element of kernel of F for arbitrary elements G in capital G. Hence, the set GK G inverse is contained in K, and hence K is normal, where K is the kernel of F. K is the kernel of F. Okay. So that's an easy justification. So I can just add this up in the theorem where kernel of phi. Let me write it like this. Then kernel of phi is normal in G, and G mod kernel of phi is isomorphic to phi of G. Okay, proof. So let's just consider a map, say F from G mod kernel of phi to phi of G. Okay. Now, how do we define this map? Such that let's say phi of G capital K is equals to phi of G. F of G capital K is equals to phi of G, where we denote the kernel of F as K. Okay, so this is the definition we would use. So what are the things we need to check? We need to check whether F is 1 1 onto and homomorphism or not. Is F well defined? Now F is trivially well defined, because if you choose two elements, if you choose, see, this is kind of obvious, because if you choose elements G1K equals to G2K, then that would imply G1 G2 inverse is in K, but that would imply phi of G1 G2 inverse is equals to 1. But again, by properties of homomorphism, it would imply phi of G1 is equals to phi of G2. But phi of G1 is nothing but f of G1K, and phi of G2 is nothing but f of G2K. So two identical preimages give two identical images. Hence f is well defined. Therefore, f is well defined. Right. So observe that we can also, move backwards, proceed backwards from the statement. Because if f of G1K is equals to f of G2K, then phi of G1 equal to phi of G2, but then phi of G1 G2 inverse is equals to 1. But that implies G1 G2 inverse is in K, but that implies G1K is equals to G2K. So I can just equivalently write these statements, and proceeding backwards just says that f is 1 1 as well and is injective, right? Okay, this is capital K, right? Okay. So we have already shown it's 1 1. Onto is very trivial, because for all elements phi g in the phi of G, there exists some element G in capital G such that Gk is mapped to phi G. So it's onto, right? Therefore, F is onto. So it's mapped via F, right? Is phi a is F a homomorphism? So what is F of G1K G2K? So it's F of G1 G2K, but f of G1 G2K is phi of G1 G2. Phi is a homomorphism, so it's phi of G1 times phi of G2, but phi of G2 is f of G1K, and phi of G2 is f of G2K. Therefore, f is a well-defined homomorphism, right? Therefore, f is a bijective homomorphism, which implies it's an isomorphism. So G mod kernel of phi is isomorphic to phi of G, right? Okay. Now observe what more can we say from here. We can say that this implies, because f is a bijection, so G mod kernel of phi must be equals to the order of phi of G. But we can write this as the index of kernel of phi in G equals to the order of phi of G. If you guys have studied linear algebra, then there's a very fine theorem in linear algebra called the rank nullity dimension theorem, where what we usually do is that we consider a linear operator or linear transformation between two vector spaces V to W. We consider V to be a finite dimensional vector space. These terms will be not known if you have not studied linear algebra. I'm just stating this for those who have studied. Then we say that the nullity of T is exactly what kernel means, plus the rank of T, which exactly means the nullity of T basically means the dimension of the null space of T, right? Rank of T means the dimension of the range of T is equals to the dimension of T. Okay. So observe that this is equivalent to this in group theory. Sorry, not this. Sorry, this. Yeah, this. Okay. Clear? Okay. Without further ado, let's dive into the next isomorphism theorem, which is the second isomorphism theorem. And this has one more name, which is called, I guess, the diamond isomorphism theorem. Yeah, the diamond isomorphism. Okay, what do we have here? So the statement, let G be a group, let G be a group, and let A and B be subgroups of G such that we have another condition that A normalizes B. Okay, if you do not know about this term, please go and view the previous lectures to have a better understanding of these terms. What is meant by A normalizing B? Then AB is a subgroup of G. B is normal in AB. What more can we say? A intersection B is normal in A, and AB by B is isomorphic to A mod A intersection. Okay, it's correct. It's obvious that since B is normal in AB, though we have not proved, I'm just stating the fact that since B is normal in AB and A intersection B is normal in AB, these two quotient groups are well defined, right? So A normalizes B. It's what's given to us. A normalizes B, but this implies simply that A is a subgroup of the normalizer of B in G. Recall from the previous lecture, we had said that if this situation arises, then AB forms a subgroup of G. But how was AB defined? So it was defined as a collection of the form AB such that A is in A, B is in B, right? So this part is obvious. How do we show that B is normal in AB? See, A is a subgroup of the normalizer of B in G. B is by definition a subgroup of the normalizer of B in G, but this implies AB is a subgroup of the normalizer of B in G, but that means AB normalizes B, so in a way B is normal in AB. That is, whatever element you choose out from AB, it will fix the set B under conjugation, right? Whatever element you choose, whatever element G you choose out of AB, G will fix B under conjugation because AB is contained in the normalizer of B in G. So B must be normal in AB, right? That's quite obvious. But if B is normal in AB, then what I just said, that AB mod B is well defined, right? What can I say about the intersection that this happens? We do not prove this directly. Rather, in due course of the proof, we will show that this A intersection B is a kernel of a homomorphism, and that then it will immediately prove that A intersection B is normal in A, and this isomorphism will hold again from there itself. See, whatever isomorphism theorem we have only one more isomorphism theorem, but whenever we need to prove any sort of isomorphism between groups, the first tool which we want to use, or which comes to use most often, is the first isomorphism theorem, and we will prove this isomorphism theorem using the first isomorphism theorem as well. What we do is that we consider a map from A to AB mod B such that an element small a is mapped to A capital B. Okay. Okay. Is this map well defined? No, it's well defined by definition, right? If you choose two equal elements A1 and A2, then A1B will be A2B. That's quite a trivial definition. So it's well defined by definition. Is it onto? That's a good question. Is it onto? So let us check whether it's onto. See, an element of AB mod B will be of the form small ab in B. Okay, so let this be in AB mod. But then observe that AB capital B is nothing but by associativity AB capital B. But B is an element of B by definition of the collection capital A capital B. So this is nothing but AB. Right? Therefore, for all A, B, capital B in A, B mod B, there exists an element A in capital A such that this A is mapped to A capital B, but A capital B is same as the element we started with, which belongs to A, B by B. Hence, therefore, phi is on. Okay, clear? So since phi is onto by acha, okay. First, we need to check whether it's a homomorphism or not. Is phi a homomorphism? See, this I should have done later, but rather it's okay. Is it's phi a homomorphism? So what is phi of A1 A2? So phi of A1 A2 by definition it's A1 A2B. But A1 A2B by operation is A1B times A2B. But A1B is again phi of A1, A2B is again phi of A2. Therefore, phi is a homomorphism. So what do we have till now? We have phi from A to AB mod B, and phi is a homomorphism and is onto. It's onto means the image of A under phi is, the range completely is the codomain, right? Because it's onto. But this so therefore this implies, therefore from first isomorphism theorem, what we have is that the domain group A mod kernel of phi is isomorphic to the image of A under phi, but that should be exactly equal to AB mod B because phi is onto. But what is kernel of phi? So if you carefully observe, kernel of phi is the set of elements A in capital A such that phi of A is 1. 1 in the quotient group AB mod B. So that's must be B. But phi of A is equals to B. This implies A capital B is equals to B. But then by definition, these are the elements A in A such that A is in B. So it's exactly A intersection. Therefore, this immediately implies that A intersection B is normal in A, right? And A mod A intersection B is isomorphic to AB by B. Okay, I guess this statement is clear. Now, why is it called a diamond isomorphism theorem? So if I observe the lattice, if you don't know what a lattice is, I'll refer to my lecture on lattice of subgroups in my playlist. So what a lattice is, how can we justify the term diamond isomorphism theorem? Basically, the thing is that if I consider a group G, then under these circumstances, which the theorem holds, AB is a subgroup of G, but then A is a subgroup of AB, and B is also a subgroup of AB. Then A intersection B is a subgroup of both A and B, but then A intersection B has subgroup 1. Observe that if I consider CC, the isomorphism holds between this edge and this edge, right? This edge comes to be isomorphic to this. So it's a sort of a correspondence among a diamond shape. So that's why the term the diamond isomorphism. See, it's obvious that AB by A, AB by B need not, or let me just say it in, not in this way. See, this correspondence can hold along this line as well, right? But AB by A is not always a subgroup, always a group, but still the correspondence holds in terms of index, that the index of A in AB equals the index of B in A intersection B in B. Okay, so the correspondence amongst index, it holds along this edge as well, but isomorphism does not hold in this edge. Isomorphism holds here according to the hypothesis we have in the theory. Clear? Okay, let's check the third isomorphism theorem. The third isomorphism theorem. What does the third isomorphism theorem say? So it says that let G be a group and let H and K be normal subgroups of G such that H is contained in K. Then K mod H is normal in G mod H and G mod H mod of K mod H is isomorphic to G mod K. Okay, so this is the third isomorphism theorem. Now proving this is fairly trivial because if I choose an element from G mod H, say G capital H, and I conjugate the any element of KH using this element, then by group operation it's nothing but G K G inverse H, but K is normal, right? So this element must be in K. Therefore, this must be in yeah. So this element must be inside K. So this is an element in K mod H, right? So we started with an element in GH, K mod H, GH, and this element comes here, right? Yeah. So it's indeed normal in G mod H, right? Okay. So therefore, if K mod H is normally G mod H, so this group is well defined, right? Then this quotient group is well defined, and this quotient group is well defined as well because K is normal in G. So what do we do? Let phi be a homomorphism from G mod H to G mod K such that an element G capital H is mapped to G capital K. Again, this is well defined by definition or by the structure of how it's given. Is it 1-1? We do not need to check it, right? Let's just prove it using the first isomorphism theorem because that's the best tool we have. So by first isomorphism theorem, G mod H by kernel of phi must be isomorphic to the image of G mod H under phi. Observe that phi is onto by definition. Phi is onto by definition as for all elements Gk in K in G mod K, there exists an element G in G, or I should say GH in G mod H, such that G mod H is mapped to G mod K because these elements depend only on G. So if I choose the coset G mod Gk, then creating a coset using that very G will get a pre-image of it. So clearly it's onto, right? So if it's onto, then phi of G mod H is simply G mod K. Therefore, what we have is that G mod H by kernel of phi is isomorphic to G mod K. What is kernel of phi? So kernel of phi is set of elements GH in G mod H such that it is mapped to GK, right? So sorry, it's mapped to identity of G mod K. The image of GH is GK, so GK should be equal to K, right? But that's the set of elements GH in G mod H such that G is an element of K. But then observe that's nothing but K mod H, right? Because these elements G, these come from K, hence these are elements from K mod H. Therefore, the kernel of K is K mod H. So this is isomorphic to G mod K. Clear? Okay. Yeah. Now we are left to talk about one more isomorphism theorem, but we are not going to get into the proof of it or the details of it. Instead, we are going to see the application of it because this isomorphism theorem actually helps us to find a correspondence between the subgroups of G mod N and the subgroups of G containing N, where N is a normal subgroup of G. And also this gives us a lattice structure of the quotient group using that of the group G. Okay. So in a way, it gives a one-one correspondence between the subgroups of G mod n and those of G containing n. Okay. So let me state the theorem. Let me get into some applications of it. So the lattice isomorphism theorem. The lattice isomorphism theorem. Okay. So it states that let G be a group and let n be a normal subgroup of G. Then there exists a bijection from the set of subgroups A of G containing n onto the subgroups A mod n, which we denote as A bar of G mod n. Every subgroup of G mod n is of the form A mod n, with A being a subgroup of G and n is contained in A. Okay. Now this is fairly easy to prove, right? This is fairly easy to prove. This sort of, you can think of it coming directly from the natural map. Okay, you can think it coming from the natural map. We'll explain it more that this exactly follows from a commutative diagram. Say it. I'm not going to just get into the details of this proof. The properties of this bijection are the properties of this bijection are for all subgroups AB in G and N in AB. What do we have is number 1, A is a subgroup of B if and only if A bar is a subgroup of B bar. Number 2, A is a subgroup of B, then the quotient, the index of A in B is same as the quotient of A bar in B bar. Number 3, the subgroup generated by the the bar of the subgroup generated by AB is equal to so it's equal to, wait, I forgot this equality. I guess it's the subgroup generated by A bar B bar. One sec. Let me just verify this once. Okay. As far as I remember, it should be A bar B bar. I guess it's A bar B bar. Okay. Number 4, we have that A intersection B bar is equals to A bar intersection B bar. And number 5, we have if A is normal in G, if and only if A bar is normal in G. Okay. Clear? Okay, so you can try and prove this on your own. There's nothing too much difficult in it. You just follow the definitions of each of these structures. What's important here is this: how can we read all these subgroups of a quotient group using the lattice of the group? Example: consider G to be Q8 and let n be subgroup generated by -1. So clearly n is normal in G. Right? Clearly n is normal in G because you can just verify this on your own. Now observe that Q8 mod the subgroup generated by -1 is isomorphic to V4. I guess we had given a proof of this previously in some lecture. I don't exactly remember, but you can view this directly from the fact that this has order 2, this has order 8, so this has order 4. So it can either be isomorphic to Z4 or V4. You just verify the fact that there is no element of order 4 in here. there is no element of order 4 here, then it will be isomorphic to V4, because if it has an element of order 4, then it must be isomorphic to Z4. But how can we study this directly from the lattice? How can we establish the isomorphism directly from the lattice? It can be done using the lattice isomorphism theorem. What is the lattice of Q8? So if you remember, it's this, K, then these all go to the subgroup generated by -1, and this go to the trivial group. What we do is that we just read off the lattice structure by decomposing the group n, that is the group which comes in the denominator, to identity. So if I consider this to be restricted to identity, in the lattice somewhat comes out in this form, right? So it comes out, the lattice is simply this part, right? So this part is the lattice. Observe that it is sort of, by lattice structure, is isomorphic to some sort of like this, right? It's generated by A, generated by B, generated by C, and coming back to 1. Observe that this is the lattice of V4, right? Right. Let us consider one more example. Consider D8 mod subgroup generated by R square. What is the lattice of D8? So the lattice of D8 is quite a bit complicated. So you have S R squared here, then you have R here, you have RS R squared here, correct? Then SR squared, this breaks down into 3 ones, this breaks down into 1, this again breaks down into 3. So the ones here should be, one should be S obviously, one should be R squared obviously, and what should be the element composed by both of these? So R square S. We should have R squared here. Then again here we should have RS here, and we should have RS composed with R square, but that's R cubed S, correct? Yeah, that's R cubed S, right? I should say the R square composed with S here, and R square RS composed here. But then all these subgroups, these go to 1, right? But here you have D8 mod R square, so we need to restrict this to identity and read off the lattice from the subgroup generated by R square. So this should be this part only, right? That is this part. Observe that the lattice is then coming out to be somewhat of this form, right? So it's yeah, subgroup here, some generated group here, some generated group here, and some generated group here. But again, observe that this is equivalent to the lattice structure of Q8 mod -1. So in a way, from the lattice isomorphism theorem, we can say that Q8 mod -1 is isomorphic to D8 mod R square. An important observation which you can bring out from here is that, observe that the subgroup generated by -1 is isomorphic to the subgroup generated by R square in D8, because this is order 2, this is also order 2. So both are cyclic subgroups of order 2, hence are isomorphic to set 2. So both are obviously isomorphic to each other, and these two quotient groups are also isomorphic to each other, but Q8 is not isomorphic to D8, right? So in a way, we have this observation of this form, like, so A mod B isomorphic to C mod D, and B is isomorphic to D does not imply A is isomorphic to C, right? And the commutative diagram I wanted to speak about while saying the concept of lattice isomorphism theorem was something of this sort, that if you, so let me just state it here, the following diagram commutes. So it basically means that if you start with the group G, then you can map it via the natural map to G mod n. But then you can map G mod n to some subgroup H via a mapping phi, and then you map G directly to H via say phi. So suppose this, I guess this is psi, right? The by commutativity means that approaching H from here or directly from here is same, And that's what commutativity means. That is, phi is nothing but psi of pi. This is what commutativity means. That you, if you want to reach a certain point, you can move from either ways. You can move from here or you can move from here. Okay. But this map is well defined if n is contained in the kernel of. Keep this in mind. That a map from a quotient group to a subgroup is well defined if the modulus of the quotient group is contained in the kernel of the map, kernel of the homomorphism. So this is a homomorphism. We are speaking about homomorphism. Okay, so this is a commutative diagram this structure is only called a commutative diagram. That is, suppose you have A mapped to B mapped to C and A directly mapped to C. So first doing, so moving from A to C from this direction is same as moving from A to C directly from here. That's sort of something which we call a diagram to commute. Whatever. Okay. So let this lecture be up to this much. In the next lecture, we will be coming up with the concepts of the silo theorems. I guess I did not complete the concept of silo theorems while we were studying group actions. We are going to complete it now. And after completing silo theorems, I guess it will take 3 to 4 lectures. So after completing silo theorems, we will be moving on to the concept of direct products and semi-direct products and so on and so forth. And then I'll try to get deep into the concept of the finite abelian groups. Okay. So meet you guys in the next lecture.